continue our conversation here and look at the next section of reaction of alcohols. So we're going to look at reaction of alcohols as nucleophiles and electrophiles. So let's take a look first at alcohols reacting as nucleophiles. And there's two ways that we're going to see that this can occur. The first is that we're going to take something like this, an alcohol, which by itself is a weak nucleophile. Okay, and that weak nucleophile can react with a strong electrophile. So we'd see an electron flow where we come and make a bond with that carbon atom. This gives us a charged intermediate, right? Because this H is still hanging out right there. So we've got a plus charge there. So putting in our electrons, you might do something like this. Got a set right there. And then you end up with this neutral charged final product. Now, side note, this thing, interestingly, is known as an ether. So we're going to see this same exact reaction in chapter 14. By the time we get to that chapter, most of the reactions are going to be a review. Now, note there that up above it says this bond is broken after the carbon-oxygen bond is made. Okay? Here, the bond is broken to make the alcohol a stronger nucleophile. So here we take a weak nucleophile and we add something like solid potassium. We could add solid sodium also, as we see in this specific case. And that would form a strong nucleophile that could then undergo a reaction that looks like an SN2, right? So here we would see SN2, right, plus or minus E2, depending on, right, all the conditions of what that substrate looks like. Now, also pointing this out, here is an ether. So you've made an ether here. But you could get some elimination depending on what this R group was and stuff here too. All right, so let's look at alcohols reacting as electrophiles. So let's take a look down here below and see this. So there's a couple ways that we can do this, and it leads us nicely into this next section. So let's first take a look at how about that primary alcohol. So let's just do an ROH like this, just make it generic so don't worry about if it's what degree of substitution it is and stuff. So let's take a look at that. And then to this, why don't we add like HBr? Okay. So by itself, remember this thing right here is not a good leaving group. It is a bad leaving group. That's right, for SN2 is what we'd say if we wanted to clarify that. All right, so in order to convert it into a good leaving group, we're going to take that H away from HBr, and then this will make that protonated alcohol. So we're going to get this guy now, right? So, okay, that's your plus charge. And here's the interesting thing about this is now this guy here is now a good leaving group, right? So you've converted a bad leaving group into a good leaving group. And then if we wanted to continue this, then we would say, well, we've got bromide in the solution because you just made it through your step number 1. So this guy's going to come around, grab a hold of that, and then we're going to kick off water there. So loss of water is typically a favorable thing. We see it a lot in biochemistry. So that plus, and now your RBr. So you make an alkyl halide that way. Now there's one issue with this, and I want to point it out to you guys down here below, is this. Is when we go through and we look at this good leaving group situation. Right, so let's just take a look at that guy. Let's start off here with our ROH. And right, so the first step of this would be, right, like how about you add H3O plus. So if you do that, you would get an ROHH plus there. So I'll give you a second to catch up here. So let's talk about that in a little bit more detail. So this is important. So here again, right, is our good leaving group. But, so there's a problem with this thing. But this is prone to deprotonation. By bases, by strong bases, right? If you take your finger and cover up this R group right here and call that an H, you've got yourself H3O plus. It's a strong acid. So anything that's slightly basic has a propensity to want to take off one of those H's. So strong bases, often remember, are strong nucleophiles. So, if you came through here and said, all right, well, let's add this stoichiometrically, and then we'll come in for a second step and we'll put in methoxide. So methoxide is going to come over and grab an H. And then you're just back to square one here. So now you have an R OH plus CH3OH, right? And that doesn't help you. So here's our goal. This is what we want to do. We want to try to figure out how can we take this, which is a bad leaving group, and turn it into something like this, which is a good leaving group, but also something that's not prone to reacting with strong bases, right, / nucleophiles. So the answer to that is on our next page, and it's really cool. It's called tosylation. So flip this thing down here and let's take a look at the next page. So this is our main goal. This is our solution to this problem. So the solution is going to take an alcohol. So here we have an alcohol. And the way that you'll see this is you'll see TSCl written there. And then pyridine. So pyridine is this guy over here, this cyclic structure. It looks like benzene with a nitrogen hanging out on it, right? And what we make in the end is, so we get HCl there plus this compound. And here's the thing that I want to just point out to you. This guy right here, that simply is a very good leaving group. Right? And it leaves as an OTS with a minus charge right there. Okay? So we're going to look at this down below. We want to talk about why. Why is it a good leaving group? What makes it good, and why is it something that we use so frequently in this chapter? So let's talk about the mechanism here. But before we jump into that, I want to take a second and I want to look at the abbreviated structure of this. And I kind of ran out of space a little bit here, so I want to zoom in, and over here on the side, let's just talk about what is this TS thing. Okay, so the way we often abbreviate this is an ROTS. Okay, so this is the same as this guy. So let's draw out that TS group here. So there's your RO group. Now we're going to come down here, and it's connected to sulfur. With a couple oxygens on there. And then we're going to put a benzene ring down here with a CH3 there. Okay? So this part of the molecule here is, we could say, from the alcohol, okay? And then this guy here, so we're going to kind of double dip. This guy down here is going to be your leaving group. Okay? Remember we said that it leaves with the oxygen atom, right? So that's going to be carried away with it. And that means that this fellow up here is going to be where we see like substitution and eliminations. Okay? All right, so now that we got that down, let's go down below and let's talk about this tosylate formation thing. So let's take a look at a reaction with just a generic alcohol here. So let's take ROH, okay, and let's react that with this compound. So plus, let's put the TSCl group in here. So The TSCl group is going to look like this. So remember, it's TSCl. So there's the Cl part, and then you got a CH3 down there. All right, so this thing has a big old scary name. Do you guys remember from a couple chapters ago when we're substituted at the 1,4, we call that para, right? So the name of this thing is para, and this is toluene, and it is sulfonyl chloride. You should recognize the name if you see it in writing and stuff like that for questions, but we just basically will abbreviate this TSCl once we get into like looking at specific reactions and stuff like that. For the mechanism, we need to know what the structure looks like. Okay, now that is going to be reacting, and then we want to use pyridine. So pyridine is our solvent here, and sometimes you'll see this just written PY or PYR sometimes. Now, the first step of this reaction is that one of our lone pairs of our oxygen comes over and grabs sulfur. And then we're going to kick off chlorine. Okay, so what we're going to get down below here, or I should say over on the other side, is our oxygen, right, with our R group here and an H. And then that's going to be connected to the sulfur and all that other stuff. So sulfur comes over here, and you got your methyl group down there, okay? And then a plus charge there. All right, now we're not done, so we're going to continue on here. So what we want to use is a base to do a deprotonation, and you know, depending on what book you use, they might use pyridine. Sometimes, like our book, I believe, uses chloride in here. That's why HCl was one of those products, but it's not a big deal. Pick one of them. So we're going to do this. All right, guys? So let's check out what we get in the end. So here's our O, here's our R, and then sulfur with the rest of this, you know, the jewelry or whatever on there, right? Remember, sometimes we draw a circle to represent benzene there. Okay, so then again, to point out, here's your leaving group. So this guy right here, later on, we're going to see this in the next page, this is going to be your LG. And we call this thing, by the way, a tosylate ester. Okay, so then what we see, and here's kind of the idea, just as a little, let's just talk about this theoretically, a little example here. So if we did like an SN2, we could have a nucleophile, right? And the nucleophile would come in and react here, and then we'd do a flow like this, right? And then that would give you your R nucleophile, right? And then your leaving group. So why is the tosylate a good leaving group? So let's take a look at it. So when it left, if we were to do this, right, it would be an oxygen with a minus charge connected to the same old thing that we've been drawing all along. Okay, so I hope that you can recognize this, and let me zoom out a little bit more here. But that compound right now has a lot of resonance. So this is a pretty stable, right, conjugate base. It has a lot of resonance. So look down below and let's take a look at that resonance. So here's your nucleophile like we saw before, right? Coming in, so there's your R nucleophile, that's just a bond, so just draw that as a bond there. And then here are some of your resonance structures for that compound. Okay, so again, that makes it a good leaving group. So the fact that it's a weak basis make good leaving groups, right? So that's a stable conjugate base. So sometimes students just get so messed up in all this because it's this big, ugly looking structure. But remember, it's just an ROTS, okay? So let's look at an example on the next page and see if we can kind of simplify the issue a little bit. So let's take a look at a couple examples. So let me zoom over here and let's look. All right, so here's what we're going to do. Let's do this. Why don't we take something like this? Let's make it interesting. So let's make it chiral. So that by itself, right, remember, is a bad leaving group. So here's what we're going to see. TSCl pyridine. Okay? Now, when we do that, we're going to form an OTS. Now, it's the oxygen that reacts, not that carbon there. So that oxygen's still going to be out on a wedge, right? So that's going to give you your OTS there. So here's all we need to do, right? I mean, we need to know that mechanism and understand it. But here we took a bad LG and we've turned it into a good leaving group. That's it. Treat it in your mind as like iodide or something, okay? Because then you're just back to chapter 6 stuff. So now let's go ahead and let's do an example and revisit some of our old problems from chapter 6. So let's throw in something like CH3O-. So that's a strong base, right? It's a strong nucleophile. Here you have kind of a secondary, we'll just call it a leaving group rather than an alkyl halide. And this is going to give us really a mixture of E2 mostly with, depending on the book, a little bit of SN2. Right? The matters who's writing the question. So why don't you guys take a second, pause this video, see if you can figure out what the products might be here. All right, so let's take a look at them. So for SN2, we're going to do a backside attack, and that's going to put my oxygen and my CH3 pointing back. All right, notice, by the way, here, this is also an ether, so we're going to see this reaction in that chapter 14 also. And then for elimination, we're looking at all of our beta positions. So we're looking at this position here and this position down here. Because we have two H's at that position over on the right, we can get cis and trans. So we're going to get our double bond here like that. That's alkene number 1. Then we're going to get our double bond in just like so. And then we get its partner in crime. And the way I do that is draw it out like this. So here your ethyl's coming up. Now it's going to be going down like this.